As well as the other specifications on the VAM differential amplifier, it has a specification on input impedance. That's very common in amplifier design. After all, you want to know what effect the amplifier is going to have on any signal source, be it electric guitar, microphone, output of a mobile phone, whatever. The specification for this amplifier is that its input impedance must be between 5k and 20k over the audio frequency range, which we're taking to be 40 Hz to 20 kHz. And this is a differential input impedance. And the differential input impedance is the ratio of the differential voltage at the input to the current flowing in. So, as shown in the circuit here, we have a differential input voltage of 1 volt, and this ammeter is measuring the current flowing into this differential input. Obviously, it's a circuit, so exactly the same current is flowing through this wire as well. This current has to flow round here. So, we can't actually plot the input impedance in this simulator. Some simulators can, but this one can't. But what we can do is work out what that current has to be, what the limits are on that current in order to meet this specification. Zin, as a reminder, is the input voltage, or the differential input voltage, to be exact, divided by the current flowing in to one of the differential inputs. And as we've seen, that will be the same current as is flowing out of the other differential input, because all current has to flow around in these circuits. Okay, if the input voltage is set to 1 volt, as I have done in this simulator here, then the relationship between the input impedance and the current measured by the ammeter is just the current measured by the ammeter is 1 over the input impedance. Therefore, for a value of 5k input impedance, we would expect the current flowing in to be 1 over 5k. This is going to be our input current. And for a input impedance of 20k, we'd expect our current flowing in to be 1 over 20k. Well, that would mean that the current measured by the ammeter should be within the range of 1 over 5k, 200 microamps, and 1 over 20k, which is 50 microamps. So, that is the specification that we're trying to achieve. It's quite difficult to measure the differential input impedance in the lab, so just getting the values correct in simulation is good enough for this design exercise. We need the current to be within those limits, okay. Clearly at the moment we are failing. The input current is too big, at nearly 503 microamps. We'll need to increase the input impedance, and that is most readily done by increasing these resistors, or increasing these resistors, or possibly both. We could increase these two resistors. Remember, they have to be the same for the differential amplifier to work. Put them up to 10k perhaps. And we could put these up to 10k as well. And we are now within the range. Are we within the range for all frequencies that we need to be? Going down to 40 Hertz. Ooh, just. Yes, just within the range at 40 Hertz. And up at 20 kilohertz. Round here, well within the range. Yes, okay, so that does work. However, you will notice that we've now changed the gain of our front stage here. The gain is now 1/10. 1k over 10k, so that's not a very good way to start your differential amplifier. You'll need a much larger gain than that. You can also see that we're nowhere near meeting the frequency response that we might want from an audio amplifier as well. We would want the audio amplifier's gain to be flat over the audio frequencies, and this one isn't. But that is a matter for another consideration. Just setting the input impedance, yes, this design would just about meet the requirements on the input impedance.